Now what we're going to do is dive into Chapter 6, which covers rational functions and equations. Starting with rational functions and expressions, let's review what a rational number is. Most simply put, it's a fraction. A number that can be written as the quotient of two expressions. They can be integers, and if we have a rational expression, then the two expressions can be polynomials, p and q. The big rule with rational numbers and expressions is that the denominator cannot be zero, because if we divide by zero, we end up with a undefined expression or equation. So we have some examples of rational expressions here, and we can see various complexity. But now what we're going to deal with a lot is expressions where the denominator has one or more variables in it. And we can also have rational functions where we have the same expression but set equal to f of x, denoting its function. Just again, as with fractions, a rational expression is undefined if the denominator is zero. Any value of the variable that would make the denominator zero will cause the function to be undefined at that point. So we can look at the domain and identify what are all the possible values that x can be, and more specifically, what x cannot be unless it would make the function undefined. So given an expression such as x squared plus 2 over x minus 3, we can see that if we set the function, or we set x equal to 3, this would cause our denominator to be 0, which would then make our function or expression undefined. So what we end up doing is just excluding 3 from the domain, because our domain can be any other value of x. A couple different ways that we will see the domain written. We have set builder notation and we have interval notation. The first one we have is x such that x is a real number. We can say that x is everything except for negative 3. X can be all numbers except for 3. Interval notation, what we do is we indicate all values of x that are less than 3, and we indicate all values of x that are greater than 3. We're skipping over 3, and we use the union symbol to combine these two sets. All values that are less than 3, as well as all values that are greater than 3, not including 3. So when we're considering domain, we only need to consider the denominator. The value of the numerator has no impact on what the domain of the function is. So we look here and we just have to consider the denominator of 2. And we have to ask ourselves, is there any value of x that would cause the denominator to be 2? Well, since there's no variable here, then it doesn't matter what x is. The denominator is always going to be 2. It's always going to be not 0. And so in this case, there is no restriction. Our domain is x such that x is a real number in our set builder. In an interval notation, we would state that it's all real numbers. Negative infinity, we can write a neater infinity, negative infinity to infinity. All real numbers. And so that's how we can indicate this domain. When we look at our next example, though, we do see that we have a variable. And so we want to think about, well, what value of x would cause the denominator to be 0? Well, in order to see that, what we can do is set our denominator equal to 0 in order to see what it's not allowed to equal. And we can go ahead and solve the equation, and we find that x is not allowed to equal 1. And we can test that. When we substitute it in, we see that that equals 0, which would cause the function to be undefined. And so we know that x is not allowed to equal 1. So we could use set builder notation and state that x is a real number and x is not allowed to equal 1. Or we can use interval notation and include all values less than 1 and all values greater than 1. Now, lastly, we see we have a longer polynomial. We have a quadratic equation in our denominator. And so we can go ahead and set our denominator equal to 0. And recall from previous chapters, in order to solve a quadratic set equal to 0, we can factor and use the zero factor property. As a refresher, remember we're looking for the product of C and a sum of B. our C value being negative 15, and our B value being negative 2. Well, the two numbers that accomplish that are a negative 5 and a positive 3. So x minus 5 and x plus 3 are our two factors. We can set our factors equal to 0. We solve both. X equals 5 and x equals negative 3. And more specifically, x is not allowed to be 5 or negative 3. Either of those values would cause my function to be undefined. So we can say that x, such that x is a real number, and x cannot equal 5, and x cannot equal negative 3. There's our set builder. In an interval notation, we would want all values that are less than negative 3. We would want all values that are greater than 5. And we would also want all values between negative 3 and 5 for our interval notation.